I wish to report to you that your grades on quiz number 3 has been adjusted. If you have any questions, please don't hesitate to reach out to me. And today we would like to recap, right? So we have done so many things, right? We've done so many things. To recap what we did yesterday, we plotted and graphed 2 to the power of x. And we concluded that the range is 2 to the power x is going to be larger than 0. Okay, larger than 0. And that's the preferred form. And what else to be covered? X-intercept, Y-intercept, right? So let's review what we did yesterday. Yesterday, at the end of the class, we plotted these points, right? We plotted these points. Just first ignore the first one, right? Let's look at the points we plotted. We have chosen numbers from negative number from the domain, which serve as input, and 0 as input, positive number as input. So positive number, negative number, 0 can all be qualified as input. So that explains the domain. The range, however, we found that no matter what is the input, the output will always be positive. Okay, so we conclude that the range is 2 to the power x. As a consequence, you can see from the picture, right? From the picture of the graph of the function that if we look at the output, right? We draw a vertical line. Each vertical line will tell us what the input, what the output. Input is 0, output is this bar above x-axis, right? Input 1, output is 2. Input 2, output is 4, and so on and so forth, right? Input half, the output is √2, right? We have done these yesterday. On this side, okay, on the positive side, okay, as the input gets to be larger and larger, right? So let me change the color. Okay, I do want to make a little distinction between the input and output. For input, the positive number getting larger and larger, the consequential output will also be getting larger and larger. Okay, and how do we describe this phenomenon? In mathematics, we have a language to describe this. Okay, what we will say, we say as, no, let me write it down here. Okay. As x approaches infinity. Well, what is infinity? Infinity is a number that doesn't exist. Infinity is a number that does not exist. But what it means by infinity, it just says the number can be as large as possible. The number can be as large as possible. If you give me a large number, I can give you an even larger number. And someone else will give me even larger number. And Kelly is going to give me even larger number. So the number can be as large as possible. So infinity is actually a dynamic process. It's to keep getting larger and larger and larger, never stop. Okay, it's something that only we human can imagine. Even the modern technology cannot really duplicate, show us that process properly, because the technology can only show finite process, right? If you guys have done programming, you know that you cannot get into those infinite loop, right? And that's the infinite process. Computer as advanced as they are can only show finite process. Sorry about that. So as x getting larger and larger, 2 to the power of x, right? The vertical measurement from the origin will also approach infinity. This is the language of calculus. This is the language of calculus. Okay, you will get to use this, but I'm not going to go more than this. I just want to see and introduce you to some concept. Okay, some basic concept, and you will see how naturally a lot of these symbols are being introduced. Number two. Okay, yesterday we have observed is that as the input gets from -1 to -2 to -3 to negative 1000, what do we see? For these input, right, the input gets smaller and smaller. All of these output, right, all of these output is getting smaller, smaller yet, even smaller, much smaller. Do you guys see that? That is shown by looking at the picture, right? Looking at the picture, that shorter, still above x-axis, shorter, above x-axis still, and shorter yet, but still above x-axis. So this number shows that it's getting even closer to 0, but never touch 0. Never touch 0, meaning that the curve will never touch 0. So in our imagination, we're going to actually see the dots getting lower and lower and lower still, but it never touch x-axis. But it can get infinitely close to x-axis from above x-axis. Do you guys follow me? All right. With that said and done, how do we describe that process? And this is how we describe that process. Okay. In this direction, as the input getting smaller and smaller yet, the output is getting closer and closer to 0, and very close to 0, as close as possible, as close to 0, but it's always larger than 0. So how do we describe that process? So mathematically, this is what we're going to write it down. Okay, so I'm going to show you. Okay, as x approaching negative infinity, 2 to the power of x is going to approach 0, but larger than 0. So these notations essentially are notations you are going to use in calculus. Okay, so I'm just giving you a little introduction. What it means is just as I just described, right? It's a dynamic process, okay, going to positive infinity, negative infinity. And we know the curve, the entire curve is about x-axis. The entire curve is about x-axis. Next, we're going to observe, what are the intercepts? What are the intercepts? Right? What are the x-intercepts? What are the y-intercepts? Could you tell me? What are the definition of x-intercept, y-intercept? These two words, actually, you can treat it as face value, right? X-intercept is where the curve crosses x-axis. Y-intercept is where a curve crosses the y-axis. So we got that name. Very good, Hazel. Okay, none, because the curve never crosses. You can say x-intercept is undefined, surely, but we really just pointed out that, see, that point doesn't exist. So an intercept is a name. I would say it doesn't exist. You can say it doesn't exist, you can say none, okay? But what is a y-intercept? Does the curve cross? Very good. It's a point, 0, 1, which is right here. Right here. Okay, so this point. So whenever I graph any, exponential curve like this, I always explicitly mark this point. And maybe I'll mark a couple more points, right? For example, I can mark this point, 2, 4. So when in the future, when you do your graph in your other classes, okay, however simple that graph is, be sure you mark a couple points. You don't have to mark all of them. Like, we have here, we have like 7, 8 of them. You don't have to mark all of them, but sporadically mark a couple. Guess what? If you do that, your professor will smile, and he or she might have a tendency to say, hey, this student really understand her trick, her trade. So let's just, and that's great, because that shows understanding. And our job is to assess your understanding in the case of giving you exams and so on and so forth. Okay, very good job. With that said and done, let's do a little summary about what do we know about 2 to the power x. Shall we? Are you ready? So we're going to summarize. Okay, we're going to summarize. What do we have here? We have a function, right? Let's see how many rows I'm going to give it to it. 7 rows, just try it, right? So for this function, f of x equals to 2 to the power x. Right? In terms of domain and range, and in terms of rules, we're gonna just give a nice summary. Input the rule, right? This is the rule. And there's an output. The output is 2 to the power x. Okay, and we graphed it. Let me clean this up. Right, we graphed it, and we're going to put that in the picture. Right, we have a nice picture. We worked so hard to get it. Right, we worked so hard to get it. Right, we plotted. We were working so patiently. Right, we have that patience to do that. We did it. And next, it's about domain. Domain, range, intercept, right? X-intercept. Could you fill in the blank? X-intercept, Y-intercept, right? The domain is from negative infinity to positive infinity. The range, 2 to the power x, is larger than 0, right? And we also have, I also want to insert that one sentence statement about domain and range. Okay, one sentence statement, one sentence summarizing domain and range. Very, very useful. Okay, this is your this is going to be your one useful tools. Okay, 2 to the power x is larger than 0 for any real number x. Okay, so I'm also going to introduce a shorthand notation for any real number x. Okay, that word has a shorthand notation, in mathematics. Okay, can be used at your disposal. Okay, so this notation is like that. It's an upside down A. It's an upside down A. So I'm going to use that symbol because I don't want my table to be overblown, to be like out of my control, because I only have so much space, right? I only have so much space. All right. x-intercept, none. Y-intercept, we know that it's a 0, 1. We're good, right? And the next function we're going to do, okay, we're going to do e to the power x. 2 to the power x is a simple function, right? I assume that I think you guys have done it before. And maybe 5 years ago, 3 years ago. So we have done a review today, today and yesterday. But 2 to the power x really doesn't get to be used very much in your calculus class. So I imagine in your previous learning experience, your teacher would say, okay, let's do 2 to the power x. Let's do 3 to the power x. And then the teacher will tell you, hey, e to the power x is about similar, right? And most of our students probably never get a chance to do e to the power x. And the teacher say, hey, please, I have done 2 to the power x for you. You have done we have done 3 to the power x for you. I'm going to give you homework to e to the power x. Go home and do it. I just wonder how many of you have done it, right? That's okay if you have done it or not. And today we're going to do it in class, okay? Because e to the power x is one of those exponential functions that's being used very, very frequently in calculus classes. I'm using a plural for your calculus classes. Okay, so e to the power x is very much used. So we must be very familiar with this function. Okay, so let's do e to the power x. Okay, so basic 1. Okay, so this should be, I believe it's number 11. Is that right? Number 11. I'm just doing I'm taking the liberty of just skipping number 10 and doing number 11. Okay. They are in different families, but I arranged them in that order for a certain reason. It's going to be revealed to you in time. Okay, it's going to be reviewed in time for you. So this function I'm going to do is y equals to f of x. This is one of the singular, very, very important function in mathematics. You will use this function not only in calculus 1, you're going to use it in calculus 2. You're definitely going to use it in calculus 3. If you're going to take a linear algebra and a differential equation, you're going to use e to the power x as well. And of course, not just e to the power x, it's a various form of e to the power x. It could be e to the power 2x, it could be e to the power negative x, e to the power x squared, all kinds of things you're gonna get to use it. Okay, you even get to use this in statistics. Okay, so very, very important function. So it's very important for us to use it. So what are we going to observe under the circumstances right here? We're going to observe domain range. Okay, we're going to observe domain. We're going to observe range. And we're going to observe x-intercept. We're going to observe the intercepts, x-intercept, y-intercept included. And of course, we're going to do the graph. We're going to do the analytical geometry part of it. We're going to do the analytical geometry part of it. Okay, so with that said and done, your teacher probably have told you e to the power x is very similar to 2 to the power x. Therefore, we don't have time to do it in class, but we're going to do it in this class because it's very, very important. So what I'm going to do is I'm going to show you the similarity. I'm going to show you the similarity. Okay, by copying the table we did for 2 to the power x. And of course, we know the rule has changed. The rule has changed. What is the difference? On this table we did before, that was, what is it? That was for base 2. Now we change to base e. So everything will have to be changed. So I'm going to keep every input stay the same. Okay, I'm going to keep every input stay the same, only change the output because all these base 2 will change to base e. Do you guys follow me? Does everybody follow me? So this is where it's similar. Okay, of course, e to the power 1 is no longer 2, it's e. E to the power 2, so we're going to make some adjustment. Are you guys working with me? I expect you to write them down. So all of these will be changed. All the inputs stay the same, okay? Output changed. Okay? Input stay the same, output changed. E. Everybody, have you made that change? Okay, so please just take your time, okay? And then this is E. What is E then? Right? E is one of those numbers. It's very strange looking, okay? I'm gonna show you its value. Okay, so we did the table, we did the rule, but we still don't know what E is, right? What is E? E is a numerical value. It has a numerical value. I'm going to show you what it is. Okay, this software only shows us 4 digits after decimal place. As a matter of fact, there are there are infinite number of digits after the decimal place. For that reason, it's not a nice, neat number like 2 and 3. Therefore, we're going to give it a specific name, call it E. But why this E is so important? Because it is not only used in mathematics, it is also used in economics, finance, in the case of compound interest. Okay, compounding interest is everywhere, isn't it? From your car loan to your mortgage loan, if any one of you have it, or maybe your parents have it, right? E is just omnipresent in all these different fields. All right, because this number is not so tidy, we give it a name. In the entire mathematical fields, okay, most of the book I have seen, I haven't read every textbook, every book in mathematics, right? In most of the book I have seen myself, E is a reserved symbol for this value. So nobody else people will no longer use E for anything else. That's how important this is. And there's a book written with a title just on E. Okay, I actually have one on my shelf, but when I need it, I will have a hard time finding it. So one day I'm going to find it. I'm going to show it to you. I'm going to show it to you. Okay. E. Okay. So I'm not going to work so hard to find it today for you today, but I will show it to you someday. So that's E. So for E, all you need to know is that it is a number approximately equals to 2.7. And the other useful fact you like to know is that E is between 2 and 3. Okay, E is between 2 and 3. Okay, this is very useful. This is very useful. So now we know we have a better knowledge about E. And then what do we do? Well, we have to finish this table. We have to plot the points, right? We have to plot the points. So for input a -3 under the new rule of e to the power x, and I got e to the power -3. You can use either one. It really doesn't matter. You can use the other one as well because they are the same. So I'm just going to mix it up to show you can use either one. Okay. Then you see if I plot points, what I'm going to do, I'm going to show you how you're going to do it. Just estimate. And we're not asking you to get the precise value, right? And this is the one, and that looks familiar. Didn't we see it somewhere else? For input half, the output is root E, not √2. I forgot to change that, right? Thank you. And this is E, and that's E squared. So I'm going to give you the tool to analyze, to do the estimate. So E to the power 3.
Professor
Okay.
Wang?
Yeah.
For the output of -3, isn't it 1/3? I mean 1 over E3.
For input a -3,
Yeah.
the output is this one or that one. They're the same.
Yeah, but over there you put, oh, okay.
I put e to the power -3.
Okay.
But you can use either. You really can use either.
Okay.
Okay, so you can, yes, absolutely, you can use this guy. So all of these numbers to us, to a lot of people who just study algebra or haven't touched mathematics for a while, it's kind of weird because we're so used to like 4, 5, 8, and so on and so forth, right? This is something you must get used to because you're going to be using E a lot in many, many different shapes and forms. Okay, so that's what I'm trying to train you guys to do. And next, we're going to plot the points. I want everybody to participate in this effort. Okay, so y equals to, I'm just going to get a program started. Okay, don't worry about why I do y equals 0, right? It's just get a program started. So I'm going to set up my rectangular system. And please, you do too. Okay, I make the fonts a little bit smaller. And then I wish you to have paper, pencil, please. Okay, so please have a paper, pencil with you. And we're going to plot points. Among all of the points in the table, which one do you think is the easiest to plot? That's right. Marco said it's the same idea as the pi symbol. Exactly. You see, pi, that symbol is reserved for pi, right? Nobody who study mathematics can use pi for anything else ever again. E is the same thing. Very good comments. Very good comments. Yep, it's about 2.7183, whatever, right? However you can remember. But in this days and time, if you type in these symbols in any, calculators, they're going to give you the value. Okay, so you don't have to worry about the value. Vincent says that the point to plot, the easiest to plot is 0, 1. I totally agree with you. So I'm going to do just that. Doesn't this look familiar with the e to the power, with 2 to the power x? Absolutely. So 0.1, 0, 1. Input is 0, output 1. So actually this point overlaps with the same point as 2 to the power x, right? And we already have our y-intercept. Wonderful. And what will be the next point you want to plot? Go easy, okay? Go easy. Don't be too hard on yourself. But I don't want to be too hard on myself. What else point you going to plot?
How about 1, e?
That's right. I totally agree with you. 1, e. But where I'm going to locate e 2.7? My answer is just
between 2 and 3.
That's right. Between 2 and 3, it's like 2.7. So it's closer to 3 than it's closer to 2, right? Vertically. Therefore, you got the point. 1, e, and then there's a dot. You put it there. 1, e. Are you guys with me? What's the next one? So we're going to plot some points on the for positive input. We're going to plot the points for input equals 0. And we're also going to plot some points that the input is negative, right? So we're going to have a little bit of everything in every area. Does that make sense? So what will be the next point you choose? How about I choose this time? I choose -1 input, okay, output of 1 over e. Then you say, how do I estimate the point for that? How do I estimate the point for that? I'm going to show you how. Okay, of course, I already have the point there, right? And this is going to be a very useful. If 2 is less than e, less than 3, then if I do the reciprocal, what will be the relationship? Are they still less than, or should it be somewhat different?
More than?
That's right. Does that make sense to you? So E is between 2 and 3. 1 over E is between half and third. So that's how you estimate your place and when you plot that point, because we only ask you to sketch it, right? We only ask you to sketch it. So when you sketch that point, for input equals -1, the output is 1 over E. So now I'm going to mark these points so far, because I want to show you the good example of marking points. Okay, so this point is 0, 1. That point is 1, E. Right? And this point is -1, 1 over E. And then we're going to continue to plot more points. Okay, shall we? Then you're going to encounter 2, E squared. How about E squared? How do you assess the place of E squared? How do we assess the position of E squared? So I want you guys to mark your points, to mark some points on your graph. And this is usually the must. And the other two you can choose, you can pick and choose, but it's always a good practice that when you graph, you plot you mark a few points. So that will compensate the imprecision when we sketch on paper, because if we mark them clearly, it's more like an architect, right? The architect, when they draw a blueprint for a house, they're not gonna to have the exact measurement. They do it in certain proportion, but they mark the number. They mark the actual number on the blueprint so the reader can understand or know how long it actually is. Perfect. Okay, Bodhi, very good. E squared is more than 4, less than 9. That's the point. Okay, wonderful. I think you got the hang of it. Okay, so with that said and done, I have to do a little bit clearing, and then I'm going to show you how this is done. Okay, I want you to be the master. I want you to be the master of inequality. Okay, they're going to earn you so many points. So if I square every side, right, that's what Bodhi did, I believe. Is that right? So E squared is between what? It's between 4 and 9. So you just estimate a point. If you really want to be so precise, grab a calculator, you know, E squared, you get a better estimate. But these inequalities are super useful for your future calculus classes. That's why I introduced them. Okay, little things like this. These are the devils in the detail. Okay, now, so the next point we're going to plot is, of course, is going to be 2, E squared. When input is 2, the output is going to be E squared. Boom. So I get another point. You see, continue, I'm going to do the other 2 points, right? So how about these 2 points? These are even harder to estimate, right? But we need to know their relative position. For example, this output is smaller than this output. So that you know the dot is getting lower and lower and lower, right? Closer to 0, but never be 0. Do you guys get a feel of that? That's the point I want to make. So on this side, if you're going to plot this point, right? Of course, you're not going to be precise, especially when we do it on paper, right? But we want to have an assessment about the relative point. So this dot is lower than the other one. And the next dot is even lower. That's what we want. That's what we saw. You guys with me? That's what we saw. Even lower. Even though this point seemed to sit on x-axis, it actually doesn't touch it. So what this shows is that it sees the limitation of these computer programming, is that it cannot show infinity. Computer programming cannot show infinity, however powerful the program, the computer hardware is. It just can never show us the, now if I stretch a little bit, you're gonna see there's some space, right? So this process keep going. You can see on this side, the dots is gonna get lower and lower and lower, yet infinitely. Perfect job, Christopher. That's wonderful. That's wonderful. So you're getting it. You're getting the hang of it, right? Perfect. You guys are great. You guys are amazing. Okay, so if I square them, so this is, if this is a squared, okay, I just want to copy Christopher's work there. Okay, so this is going to be squared, right? And this is a quarter. And this is 9. Wonderful. So this will help, right? Between quarter and 1/9. But these numbers is the application of these numbers go beyond just the plotting. You probably get to use this in chapter 11, calculus 2. Okay, a little details, but it's going to make a big difference. All right, so with that said and done, we get these dots and we have put on our thinking cap and our imagination is going, right? So shall we connect the dots? Shall we? We're connecting the dots. So I want you guys to connect the dots on your paper. And what do we see? We see a curve similar to 2 to the power x, indeed. But we gain so much in the inside, right? Because there is some minor differences. There's some minor differences, and those minor differences is important. Why they're important? Because typically exponential function is to describe exponential growth. For example, as currently we are in pandemics, the virus grows exponentially. Okay, if you keep plotting the numbers each day, people get infected, get tested positive, you will find it's going to be an exponential growth, right? With a different base, right? If base 2 or base E, the number of people could be impacted, could be very different. So we're talking about real world, real application. And of course, we're not going to do the real application. That's just not something we're going to do today or anytime in this class. But you see the exponential growth. They have similar shape, a lot of similar properties, but they're not exactly the same. They're not exactly the same, okay? All right, so without further ado, once again, what do we see? If the input gets larger and larger, what happened to the output? The output gets to what? Higher and higher yet. How do we describe this? I just introduced a little calculus for you. As x approaching to positive infinity, e to the power x also approach to positive infinity. Is that right? So let's write it down. Okay, so as x approaching infinity, e to the power x approaches infinity. As x approaching negative infinity, what does e to the power x approach to? This is the language of calculus. Just there's few phrases. We look at the curve, right? As x approaching negative infinity, right? Let me use the green. As the input approaching negative infinity, what happened to the red dots? They're getting lower and lower and lower yet. But always above x-axis and never ever touched it. Never ever touched the x-axis. So how do we describe that process? As x approaching to negative infinity, e to the power x approaching 0, getting very close to 0, but above 0. You see how naturally that symbol is being introduced, right? Naturally, and of course, you put a negative sign, it will be from below 0, right? So you get that. You guys are smart. Okay, so a lot of these symbols is really introduced. And Vincent put x larger than 0. What does that supposed to mean? Are you inferring so what are you referring to? Vincent, you want to say something? You say x larger than 0. What is that referring to? You said x value never reaches 0. X is the input. Range. Are you referring to the range? But if you're referring to the range, in this context, that's right. That's right. You need to specify what is the input and what's the output. This is the whole point. Okay. At the beginning of the semester, I introduced input output. I'm going to consistent doing this. Input is X, output is Y. In your past experience, we use a lot of X, Y, stuff. Now I'll give the X a new meaning, which is the input. Well, but you don't have to call it X. The output is Y. Very good. So I'm glad. You see, your question are really, really good. Really, really good. But we need to be very specific, right? So in terms of domain is about X, right? The input in our case, the way we set it up, right? So from negative infinity to what? To positive infinity. Well, what about range? You guys have said it, right? You are so close, but we need to be concise, right? So you can say y is larger than 0, but you also have to tell me that y is e to the power x, and that will be complete. Or you can just say e to the power x is larger than 0. Okay. And of course, you can also say f of x. All these are different ways you can say it. Okay, I would typically like to choose the easy one, the simplest one. Which one of these expressions do you consider would be the simplest one? This one. Most straightforward. So now let's create that one sentence. One sentence, domain and range. What would that be? E to the power x, sorry. Where did I get that? E to the power x is larger than 0. What? For any real numbers. For any real number. Okay, is that grammar okay? You guys follow me? And the entire picture reflected that. The entire picture reflected that. Right, so you have a little taste of calculus notation, and of course we still keep our focus, right? Domain and range. How about intercepts?
Professor, on the previous line, for any real number x, maybe?
Oh yeah, I missed x. Thank you.
You're welcome.
Very good. Please pick on me. Okay. Everything must be specified clearly and well. So what is the x-intercept? What is the y-intercept? Look at the picture. We're patiently building our foundation. So what will be the x-intercept? What will be the y-intercept?
The x-intercept is none.
That's right, none. Doesn't
The
exist.
y-intercept would be 0, 1.
Comma, yes, perfect answer. Wonderful, wonderful. Okay, so we done the picture, we done the domain range. Shall we summarize this? Shall we? Put that in our summary? Yeah? Yes? No.
Yeah.
Let's do it. Remember that summary table we did, right? For 2 to the power x, right? So now it's time to put them together. You see, this is how we study. If you have the time, energy, you want to systematically, as you learn new things, you summarize, compare, left and right. This is how you're gonna do your mathematics. Okay, so for e to the power x, everything stayed the same except the base. You see that? The picture looks similar. Similar, we can only say similar. Can we say they're the same? Can we say they're the same?
No.
Why not? Because they have different values, right? They only have one point in common, right? Other points will be some are higher, some are lower, right? So how about domain, range, one sentence, x-intercept, y-intercept? All of these are exactly the same for e to the power x. This is the sameness. This is the similarity your former professor or former teacher refers to. But next, I have a question for you. If you put these two curves in the same rectangular system, what's going to happen? Right? So my question is, graph 2 to the power x e to the power x in the same rectangular system. How are they positioned? Positioned. Right? We know the tables are similar, the graph is similar, but what makes a difference? And why recognize those differences are important? We made two tables, right? We made two tables. So let's compare these two tables. Right? So where's my 2 to the power x table? My 2 to the power x table, where is it? Right here. That's my 2 to the power x table. Right? I'm gonna put them next to each other. And you notice that these are basically the same inputs, right? We have the same input. Let me make the font just a little bit smaller. 125%, right? The two tables next to each other. Inputs are exactly the same. What happened to the output? If you compare for the same input a -3, for 2 to the power x, right? So this is for f of x equals to 2 to the power x. 2 to the power x. For the same input, -3, one output is 1/8, and the other one output is 1 over e to the power 3. Which one is larger? Meaning which point is higher, right? Which point is higher if you draw the vertical line. So which one is larger? Is 1/8 larger or 1 over e to the power 3 larger?
1/8 is larger.
1/8 is larger. Very good. Very good. Okay, so you can keep comparing these numbers. If you do these comparison, we know that half is larger than 1 over e. But how would that be reflected on the picture? We have an overpoint. We have a point that overlaps, right?
Be
And then we have-
slightly
Sorry.
bigger.
Go ahead.
It'd be slightly above E.
So
power
one
x.
piece is slightly above.
Yes.
The entire curve is above.
No. Only the negative x numbers inputs would be slightly above.
Only for the negative inputs, one is high, 2 to the power x is higher. How about for the
Yes.
positive number?
E to the x is higher.
That's right. Let's see. Wonderful. You do have a vision, right? So next, we're going to graph these two on the same graph. 2 to the power x. Okay. I'm going to first graph 2 to the power x. Okay. So allow me just to make a little adjustment. Okay, everybody, I want you guys to get into action. Okay, if you have calculators and you want to use it, it's okay, no problem. All right, so this is 2 to the power x. Okay, I'm going to make it just a little bit larger. This is 2 to the power x. And the next graph I'm going to graph is e to the power x. Okay, so are you ready to see the comparison? You see the red, right? The red is e to the power x. The black is 2 to the power x. The red is not always higher. The red is higher for positive input, overlap at a 0 input. And the red is lower than 2 to the power x on the negative input, exactly as you anticipated. It's not entirely higher, but both are increasing, aren't they? Both are increasing, aren't they? And they have one common point, which is 0, 1, right? Yes? Is everybody with me? Why is this important? Why is this important? Yes, for your calculus class, e to the power x is very important, super important. 2 to the power x is important. Different bases. You can see for the same input, for the positive input, e to the power x is higher. That means in terms, if you talk about the spread of the germ, if you have an exponential growth for a germ, e to the power x, and the other one is 2 to the power x, the e to the power x spread much faster. Okay, so next I want you guys to make some inference. Okay. How about 3 to the power x? 10 to the power x. How would you position them in the same picture? How would you position them in the same picture? Could you try it? No penalty. Only gain. How would you position them? Imagine these are different viruses, okay? They're all exponential growth or cancer cell growth and so on. They're all exponential growth. Different bases make the difference. E is 2.7, which is greater than 2, right? Very good. Keep going. 3 to the power x will go about E, right? So on the positive side, it's going to be steeper on this side. On the other side, on negative input is going to be but they're all going to be positive, right? So I'm going to give you just a little bit more time, 1 more minute. I want you to think about how you would sketch. Okay, I know you might have calculator, but put on your thinking cap before you use the calculator, if you will. And just after 1 minute, I'm going to graph 3 to the power x, 10 to the power x. We don't have time. We really don't have time to do, in that kind of table setting, for 3 to the power x. But I know you already get it. And 10 would be even higher. Yes. Are you guys sure? Are you sure? When you are absolutely sure, three to the power x and 10 to the power x will have lines that even farther away. Farther away from x axis, from y axis. You said farther away from y axis. Okay, so let's see. Are you ready? So next we're gonna graph 3 to the power x. Right? So what color shall we use? I'm gonna use green. That's 3 to the power x. 10 to the power of x. What color shall we use? Shall we use a blue? Why not? They're closer to y-axis. More away to the x-axis. They're closer, right? So the blue is 10 to the power x. And the green is 3 to the power x. I hope that's clear. Right? Each is closer as the base increases. Each is closer to y-axis. It becomes steeper. Steeper means what? For the same input, the output is even larger. If you think of it from the perspective of exponential growth of any virus or cancer cells and stuff, that growth is dramatic. Okay. And oftentimes the mathematical models for these, for pandemics, they're always exponential growth. They're always exponential growth. It's actually scary. It's actually scary, okay? You don't want to have a 10 to the power x exponential function for that. We don't want that to happen. Of course, nature has its own way, right? So in terms of exponential function, the larger the base, the faster the growth, Okay, so, but without further ado, so we see all 4 functions, they're all increasing and they all pass the same y-intercept, right? They all have the same domain and same range. How about that? But can we say every exponential function is an increasing function? Okay, to answer that question, okay, but don't worry, I'm going to write down the question. Okay, did you guys write it down? Because I'm going to clean it up. I'm going to clean up the board. Did you write them down? Okay, I assume the answer yes. Okay. Okay, thank you. All right. So with that said and done, we talk about, this is, let's put the summary together. Okay, let's first put the summary together, right? So we did the summary, and we did the summary for 2 to the power x, e to the power x, and 10 to the power x, right? So we can continue to make that table. So give me just a little bit time to set that up. right? So I'm going to insert 2 more columns. I'm going to make 2 more columns for 3 to the power x, right? 3 to the power x and 10 to the power x, right? In our summary. And they're so similar. They're so similar. So they're going to have the same domain and range, intercepts, boom. Only the picture has some minor differences. So this is 3 to the power x, 3 to the power x, and this is 10 to the power x, and that's 10 to the power x, right? So we've seen that. But in terms of picture, right? In terms of picture, so I'm going to put these pictures in place, right? I'm going to cut down some pictures, and I want you guys to take this opportunity to set up your summary.
Flashcard.
Yeah, flashcard or whatever. Okay. And so that's 3 to the power x, right? That's 3 to the power x. And what else? 10 to the power x, right? 10 to the power x. We see all these similarities, right? We see all these similarities. All these points of interest, and I'm just going to change the color. Okay. All right. Summary, they're all similar. We know one, we know all. We know the differences when they're together, right? My next question is, what is all of these functions together, we actually call them, there's a family of function we call exponential function. Okay, the family. Okay, the family. What is that family? The family of exponential function, exp functions, exponential functions, right? So these are the shorthand, and we have summarized them all. Right, we have summarized them all. But how do we describe the family? This is how we describe the family. The family is often written as b raised to the power x. Okay. But we have specifics on the family space. So b must be larger than 0 and not equals to 1. From all of these pictures, and we know the concept of increasing function, could we say any exponential function, when we talk about any exponential function is increasing? Can we say that? I don't want you to answer the question right now if you're not ready, okay? Because I do want to introduce you another very useful exponential function, okay, which also falls into this category, which is e to the power of negative x. So this is the function, 175%. Okay, so I'm going to make that a little larger. This function is also used a lot in your calculus classes. Then you say, does this belong to the family? Does it belong to the family? The answer is yes. Okay, the answer is yes, because e to the power negative x is really 1 over e to the power of x. And the base is larger than 0 and not equals to 1. Therefore, this guy belongs to the family. Belongs to the family. Belong to the family of exponential function, which is right here. And now I would like to go to graph this function with you. Everyone, please roll up your sleeve. Let's do it. We're here already, right? So what I like to do, we can take a little shortcut. We can really do take a shortcut because we are here, right? We have e to the power negative x, right? This is a new rule, right? We're going to graph a new function. So we can kind of borrow what we did earlier, okay, and make some changes. So on the one hand, you see the similarity. On the other hand, you see the impact of that minor change. Okay, so let's see. I'm going to make this just a little bit smaller. Okay, so I'm going to copy this table, which is for e to the power of x. Okay, and make it 175% again. Does everybody follow me? Okay, all of us are going to do the groundwork. On this function, instead of this table is for the rule of e to the power negative x, e to the power x. Now I'm going to change the rule with just one change, a negative sign in front of it. I will keep the same input. And what will happen to the output? What happened to the output will be complete change. Okay, so let's apply this rule. I want you guys to do one by one. One by one. New rule, new table. New rule, new table. Okay, take an example. Okay, we're gonna keep the same input. Okay, we're gonna keep the same input. Okay, so the inputs stay the same. Output will have to be different. It will be different. Okay, so new rule. Forget the first row for now. If I plug in the input at -3 here, what would it be here? Well, x is replaced by
Positive 3.
That's right. It's going to turn into a +3, right? Because the negative of -3 is going to be positive. So this is going to be e to the power 3. So for input -3 with the new rule, which is just a little minor change in the power, we get input at -3, the output is e to the power 3. So could you guys continue to do the rest?
Yes.
Marco says, would the graph just flip? How does it flip? I think your sentence hasn't quite finished. You're getting there. You're getting there. I can see. You're thinking mirrored. Yes, mirrored. Mirrored. How is it mirrored? Horizontally, vertically? You just need a few more words to complete that sentence. You have great intuition. Very good. Very, very good. Okay, so for I want you guys to just do the due diligence. Okay, this is going to be -2. And that turn into e squared. Input a -1. Negative of -1 is -1. Just take your time to do that. 0. -0 is still 0. So this equals to 1. So we get to put all of these for our new points. That point looks familiar, right? And this is a half. -1/2. So that's gonna be 1 over square root of e. X is 1. So this is gonna be 1 over e. And this is 2. One over e squared. Last one. What happened? Shall we plot the points? Let's do it, right? Let's roll up our sleeve. Let's do it. And but this time I'm going to do something special with you. I'm going to take the curve that we plotted for e to the power x, and we're going to plot e to the power negative x on the same picture. Okay, this is e to the power x already. This is e to the power x, we know that. And next, we're going to plot all of these other points. We're going to, of course, we're going to use a different color. And over here, we're going to plot all these new points for e to the power negative x for this new rule. Let's see what we get. Which one is the easiest to plot? Well, 0, 1 is the easiest to plot. That's a common point. Okay. And what is the next easiest? Negative 1e, if you may agree. Okay. So if the input is negative 1, the output is e. I'm going to use a different color, green dot right there. Okay, so this is the negative 1 comma e. This is negative 1 comma e. Let's how about 1 comma 1 over e, right? Input is 1. Output is e is 1 over e. The next dot, it goes there. So if you put all of these points on the same graph, right? What do you get? What do you get? Input a negative 2. My green. And we got a picture already. We got a picture already. Marco is so close. I just need you to be a little more specific for us. Okay. Do you think we can connect the dots? E to the power negative x. Not inverse. Okay, I'm referring to the line you flip over. Okay, so I'm going to use a red. I'm going to use a green. This is e to the power negative x. Is it increasing or decreasing? Is it increasing or decreasing?
Decreasing.
I mean, e to the power x is increasing. Is e
Yeah.
to the power negative x is also increasing?
No, it's decreasing.
Decreasing, right? Decreasing. So what statement did I make there earlier on? Earlier on, what statement did I make there? Could we say any exponential function is increasing? Can we say that? False.
Yes.
would it be just flip across the x-axis? No, it flip across the y-axis. Okay, reflecting with respect to the y-axis. So that's words I'm waiting for. Reflecting is the right word. Yes, Marco. It's that's right, over y-axis, right? It flip over y-axis. Okay, so this is the line, it flipped over. Okay, it flipped over. Okay, very good. So that statement is false. Okay, that's because sometimes the exponential function is increasing, sometimes it's decreasing. Now, can we put this in summary as well? Can we put this in our summary as well for e to the power negative x? I think it's absolutely necessary, especially because this function is so useful. It's so much being used in calculus class. So I'm going to add another column, okay, in our summary. Okay, so I'm going to put it here. And then of course, this is a no, right? So I'm going to insert a column here. This column, okay, is for f of x equals to e to the power negative x. The rule has been changed, just a little tiny little bit. With the change the rule, we got a new picture. Okay, negative x, sorry. Okay, negative x. And how does the picture look like? The picture, I'm gonna change the graph. Okay, e to the power negative x. Okay, I'm gonna change the color to be purple. E to the power negative x. And you guys can certainly do 2 to the power negative x, 3 to the power negative x. Those are certainly my homework. Okay, I'll give you homework on that. Okay, so you can reflect on this, right? So in summary, in terms of this family of function, in this family of function, b is larger than 0, not equals to 1. So what makes it increasing? What makes it decreasing? What makes it increasing is that if b is larger than 1, b to the power x would be increasing. Is increasing. Oh, sorry, this typesetting. Okay, I have this. I always have to switch between the modes. Okay, math mode and text mode is increasing. Okay, we see these examples at 2 to the power x, e to the power x, 3 to the power x, 10 to the power x, and so on and so forth. All of these bases are larger than 1. However, if b is larger than 0 and smaller than 1, which in the case of e to the power negative x, in this case, the base is what? Base is what? Base is 1 over e, less than 1, right? And in the case of 2 to the power negative x, the base is half, right? So in this case, instead of increasing, it's decreasing. So that's a summary. Your homework, of course, I ask you guys to do 2 to the power x, 2 to the power negative x, 3 to the power, just everything we've done in class, I want you to do it over by yourself. Okay? And this is, in terms of playing basketball, you need to do 10,000 hoops to be the master. You don't need 10,000 hoops to be a master of this stuff. You just have to do it again. And maybe a couple more times, but it will never reach 10,000 hoops. You never reach 10,000, not anytime soon. And then you will be the master of this material. Farouz, you want to say something?
Yes.
Please.
I noticed the power of table. You are organizing everything and helping us to, create our cheat sheet and see the connection relationship and using the family, the word, right? I just noticed the domain range X, Y intercept are going to be same for this new one you created.
Are they the same? I haven't finished. I haven't finished the e to the power x, right?
E to the power of negative X.
E to the power negative x, right?
Yes.
Is this going to be the same? Absolutely. You see that curve is still above x-axis, right? Yes?
And that's why you said family, right? The
That's
family
right.
of,
This is a family. Okay, I will send you guys a PDF file on this. Okay, I may have to break up the table. But I want you guys to do this on your own. But I'm just showing you this example just to how to summarize, right? Because from these summaries, you see so much in common and so much not in common. And when you put these curves together, you see which one is higher, which one is lower, when, right? And what's interesting to point out is that in your calculus class, you probably won't get to use this function much. And these are the two functions you're going to use a lot. A lot. I mean, a lot. I do mean a lot. Calc 1, Calc 2. Calc 3, into, linear algebra, differential equation. Yes, you get to use them a lot. But depend on your fields. If you are like economics, or if you guys are computer science, but if you're in computer science, you could be working in different fields. You could be writing program for a financial firm, right? And in those cases, and so you do need to get familiar with the differences and similarities and input output, that sort of thing. Okay, but they're all here, and you got the tool to how to analyze them. Okay, any question? Any question? On your homework, I'm asking you to do 3 to the power negative x, 10 to the power negative x. Right? It will be an interesting drill. Will be an interesting exercise. Right? So you're going to be fortifying what you have learned. Be fortifying what we have learned. Do you guys have any other questions? See domain range, right? Now we get to know E. In calculus class, you got to use E all day long, every day, all day, every day, from beginning of semester to the end of the semester, and then next semester start over. Of course, for different settings, Then you'll say, how about these 2 to the power x, 3 to the power x, 10 to the power x? Unfortunately, they don't get to be used very much. No. Okay, so far so good? So far so good?
I say yes.
Any other questions? All right, so if you don't have any questions, right, so we have these summaries right in front of you. I wish to tell you, number one, I have adjusted your grades on quiz number 3. Okay, if you have more questions, please let me know. And once again, I apologize for my mistake. And number 2, make sure you truly understand the material. You get what you got points given to you because of my mistake. But it's most important you know what's right, what's wrong. And the next one is that some people ask me some questions about the homework. Okay, you should expect one more quiz this week. If it doesn't come out today, it should come out tomorrow. Okay, I need some time to make them. So if you look at these exercises, I actually have I recorded the lecture. I recorded the office hour on this material today. So I will post them as soon as possible. but I don't know if you guys get to see it. You guys might get to, you guys might be sent a link as well, but I'm going to put it organized on week 2. Okay, on week 2. So now, as of now, I'm going to show you the link. I don't know if you guys have any questions on these. In terms of watching the past recording, as soon as they're available, you probably should see it, right? Do you guys see this Canvas page? A cloud recording. Okay, so all these recordings, as soon as they're available, you can see them now. You don't have to go to module to get that recording. You can if you want, because as soon as I get time, I will download these files. I put in organized under the title. So that's for our convenience, because I will have a title for what this video is for, what is this recording is for. So that way we'll give you some, pointers as, what the subject matter is being addressed in that particular recording. Okay, but otherwise you can get you can go by the dates. If you miss any classes, but today's recording is not going to be available anytime. It's going to be available a little later. So that's how I archive this information. For office hours, as much as possible, if certain topics is useful, I will record it, and I will also put it in the module for you guys to view. And I will also indicate the title. I'll indicate the title, right? The title may not be like super close, but as close as possible, as close as possible. Do you guys have any other questions? No? All right. We still have some time left. Our class ends at 50. And do you guys have any question you want to ask about your homework?
Oh, Professor Wing, I had a question. So are the quizzes, the past quizzes available to see what we got wrong?
Yes, they are available now.
Oh, okay, thank you.
Yeah. So usually the past quizzes, I will usually wait a little before the answer is available to you, just in case, some special circumstances, comes up. But I will make them available so you can see you can see. Typically, what's going to be available is your answer versus the correct answer. And of course, as you know of, I make mistakes. I do, right? Because all these quizzes, I make all of them myself. And I make it in such a way it reflects my lecture and reflect my note, reflect your homework in that sense. And I constantly have to make some changes. I have to make some changes because every semester is different. So I always have to make those adjustments. Along the way, I will make mistakes. If I make mistakes, and I will, you have seen the example I have done in the past. And for quiz number 3, I will give you the credit and address the mistakes. And the purpose for doing this, I want you guys to really watch the lecture well and have a gain understanding. And I hope that you guys will feel like you don't have to memorize so many things anymore because you understand it. That's the goal that I shoot for. And right now we're in exponential function, and then next week we're going to be addressing inverse function. And then we get to the logarithm function. And after that, we're going to get to trig function. Okay, so we're going to have a comprehensive of all of these functions as different rules being studied, and then we get to the rest of the semester. We get to the rest of the notes. Along the way, your homework may be assigned from letter pages according to, I feel like, okay, I need to check on this guy. I need to check on this, check on this thing to see if you guys know how to do it. Okay. I think we're done today. Because I don't want to start something new and then we can't finish.
Professor, if you have time and class also is here, maybe we can make a kind of decision or idea for the next couple of weeks, I may also add the Math Study Center hours. I am over there. So if the students need to refresh their, fundamental math and all this basic algebra here, there, they need to catch up. They can stop by in the Math Study Center. Is that a good idea for the next couple of weeks? We try, see what happens.
Of course, of course. Did everybody hear what Farouz is saying? He's very eager to help you guys. He's very eager to help you guys. And I really appreciate him to be around. So please pay attention to the information he sent out to you, and he's available at Math, Study Center. He attended both of my classes, and one, I have, two Math 180 and two, support classes, and he's really, really trying to be very, very helpful. So Angelica was asking what days and hours is Farouz available at MRC. So Farouz will answer that question for you. I think.
Yes, I'm gonna, probably I'm gonna be a little bit active here to write on my board, and interested students, you can take a picture of it, or it's easier for me than typing it here, there. So it is Math Study Center, right? MSc online. And so, of course, my name, you want to ask for me to help you guys. We have many other tutors too. And then Monday, Wednesday, and Thursday, easy, 3 to 6 p.m. You can find me today, 3 to 6 p.m. And the Fridays, if afternoon is difficult, Fridays, you can find me from 10 a.m. to 4 p.m.
Great. I think someone on the chat asking Farouz to send a message to Pronto or something.
Yes, I did once, but nobody responded, or I can probably.
Well, if you could send it through Canvas as a message or Pronto, that way we can just have it on in the inbox, exactly.
Yeah, inbox, really good. Don't we like these communication channels?
Many of them, absolutely, yes. Just
yes. We in these platforms, and in addition to discussion board, I think discussion board doesn't seem to be much used because people just liked the spontaneous responses. That's okay. I like it as I like to use Pronto as well. The other day I was answering a question. We were at a restaurant. I just write it on the tissue paper, and I can just give you an answer right there. And it's my great pleasure to help you guys. Okay, and I'm not gonna have say, oh, this is my dinner time and this is my, just whenever I can. Okay, you don't bother me, and I'm delighted to help. And I think Farouz probably feel the same way, right? Whenever we can, we will give you as a response as soon as possible, right? But if I'm driving, I'll tell you, hey, I'm driving. Then I know you guys understand. But if I'm not driving, I have time, whether I'm waiting in a doctor's office or I'm in a restaurant or I'm on the beach. Sometimes we do take a walk on the beach. I get a message, I can answer the question, take a picture and send it to you. How about that? Right? So this is something whenever I can, I'm delighted to do for you. I like to do it for you. I want to see you guys success, okay, to be successful. All right, so Farouz, you just continue to send your office hours because not everybody can get it that time. And,
yes, I guess I believe because maybe the class cannot see my board clearly. Is that the case? Because when we are sharing the screen, then the student cannot read the board. Is that true? Professor, can you see it clearly? Because
I can see.
Okay.
Yeah, I can see.
Okay.
That's not a problem. And
Okay.
our Pronto can also record video.
Right. I'm gonna send it to Pronto too, so everybody have the information. And this,
Absolutely.
yeah, these hours are from my other classes. So if you see other students, you need to be patient until we see in the next couple of weeks how is the reaction about this window of time, and if we need to do something, some modification, me and professor will discuss that to see how we can reach out and help you more.
Wonderful. So I will see you guys on Monday. Okay, that will be week number 3, and do expect another quiz, and I'll send you a message as soon as they become available. Oh, you see, people are sending. I think some people are copy and paste your previous message on office hours, and they posted on the
Perfect. That is
on the for
good.
Farouz. Thank you so much.
Very
I'm
well.
gonna turn off the recording, and I will see you guys on Monday. If you have any question, please, any question, don't hesitate to reach out to me or to Farouz. And we're just here to help. All right. Have a great weekend. Okay, stay at it. Okay, you can make it. You can do it.